Hello everyone, Morgan coming back at you. We are on page 14 of the gases outline for AP Chem, and we've been talking about Thomas Graham and Graham's law, and Graham's law was that the molar mass really, of gas A over the molar mass of gas B will equal the velocity of gas B squared over the velocity of gas A squared. Okay? Now we can use this to determine molar masses and the rates at which gases flow, things along those lines. So uranium hexafluoride comes up often in these examples because that was what the uranium we used during World War II was converted into for separation purposes to find the U-235. So if F6, uranium hexafluoride, flows at 15 milliliters per minute, and you have a second gas, which would be unknown, at the same temperature, flows at 43.92 milliliters per minute, what's the molar mass of the second gas? Well, the first thing that I can tell you just by looking at this is that that second gas is an awful lot lighter than the uranium hexafluoride because its flow rate is much higher. Okay, so mass A over mass B, velocity B squared over velocity A squared. Now, I am going to call B the UF6, and A is my unknown. So I can rearrange this so that the mass of A equals the velocity of B squared over the velocity of A squared times the molar mass of B. Now, the uranium hexafluoride is 15 milliliter per minute, and that quantity has to be squared. Its molar mass adds up to 352 grams per mole. It is a hefty molar mass. And the velocity of A was given as 43.92 milliliters per minute, a quantity which has to be squared. These units are going to cancel. And this is going to come out to be about 41 grams per mole. Okay? That's a pretty straightforward question. I would imagine actually on an AP exam that is more of a thing you would see in a multiple choice than in a free response. Now, a much more relevant question. How much faster does nitrogen gas flow than oxygen gas at the same temperature? So, I'm going to take my mass of A over my mass of B, molar masses, velocity B over velocity A, and these are squared. And what I'm going to do is take the square root of the whole thing and say that the velocity of B compared to the velocity of A must equal the molar mass of A divided by the molar mass of B, and I take the square root of that. Okay? Now it's time to actually do some reading. How much faster does nitrogen flow than oxygen? So, since nitrogen is the one compared to oxygen, I'm going to make nitrogen B. And A would be O2. So now the molar mass of A would be the 32.00 grams per mole. Then I'd have 28.02 grams per mole for the nitrogen. And I'm going to take the square root of that. And I got 1.069 times faster. And that actually makes sense to me because the nitrogen should be moving faster because it's a lighter molar mass. It's a lighter gas. Okay. one more slightly different example. If water vapor flows at a rate of 25.0 milliliters per minute, what rate will helium gas flow at the same temperature? All right, so mass of A over mass of B. Yeah, I keep using A and B. A lot of books would just use 1 and 2. It's fine. All right, so now I'm looking for a velocity. Okay, I have two things. I got water and I've got helium. Okay, now water vapor flows at this rate. Okay, so I know a lot about it. Okay, and helium, I want to know what rate it flows at. Okay, so because of that, I'm going to call helium B. I call water A. The reason I've done that is algebraic. I move that velocity of A over to the other side. Okay? Now, velocity of B squared equals mass of A, that's water, that's 18.02 grams per mole. B helium is 4.00 grams per mole. Velocity of A squared, 25.0 milliliters per minute. Squared. That cancels that. Velocity of B squared is 2815 milliliters per minute squared. So I take the square root, and the velocity of B is about 53.1 milliliters per minute. And it should be going a lot faster because helium is a lot lighter than water is. Okay? All right. So those are our problems that are dealing with Graham's law. Okay? We will start the bottom of this page actually in our next video because it will go on for our next topic. All right, Morgan, signing off.